Hello, everyone, and welcome to today's OSMINE webinar, Less Waste, More Metal, the Solutions That Work, which is brought to you by OSMINE member Thermo Fisher Scientific. My name is Tammy Pisani, and I am the OSMINE State Manager for Queensland, and it is my pleasure to be your host today. Before we begin, I would like to acknowledge that I am hosting this webinar from Brisbane and acknowledge the traditional owners of the lands, the Yagara and Turrbal people. I also acknowledge any traditional custodians of the various lands on which we're all working today, and any Aboriginal and Torres Strait Islander people who may be attending this webinar. So welcome to everyone. From Thermo Fisher, today I am joined by John Rutter, Business Development Manager for Mining and Mineral Processing, and Garry Noble, Senior Product Applications Specialist. Together, they're going to deliver a presentation that will inform attendees on how Thermo Fisher technology is enabling mining operations to make faster and earlier decisions that improve ore recovery and productivity, unlock marginal resources, and enable flow on benefits impacting processing, tailings, and water, which are all important in topics in their own right. I should note for everyone attending that this webinar is being recorded, and we will make a link to this recording available to all attendees, and it will also be on OSMINE's YouTube channel as well. So with that, I would like to now hand it over to John. John, the audience is yours.
Okay, yeah, thanks, Tammy. Look, thanks for joining us. As I said, my name's John Rutter, and I'm joined by my colleague, Garry Noble. Today, we'll discuss less waste, more metal, the solutions that work. Okay, foundational to describing what we believe in is our mission, to enable our customers to make the world healthier, cleaner, and safer. Our mission is at the heart of everything we do and is the foundation of what we do and why we do it. So Thermo Fisher is probably more well known for our life sciences, bio, pharma, and medical services, but we are also one of the world's most respected and largest suppliers to the mining and mineral processing industry. Last year, we generated over $44 billion of revenue and have a market cap of $175 billion. So look, we're not going anywhere, and if you want, that's your insurance policy with Thermo Fisher. But as a guide, like Glencore, one of the world's largest mining companies, has a market cap of about 90 billion. So Thermo Fisher, we're roughly twice the size of Glencore. What this does allow, though, is Thermo to have one of the industry's best innovation and R&D groups. And last year, we put $1.5 billion back into R&D. But what this does allow is continuous support, development, and commitment to delivering quality products that will make a difference to an impact to your operation. So focusing on mining and minerals, where do we operate? Well, the solutions that work range. They kick off in the exploration stage. We've got handhelds and lab equipment through to bulk online analyzers prior to grinding, because that's where one of your major cost drivers are. Then we move into the process plant. We've got samplers, analyzers, instrumentation, probably where most of you may already recognise Thermo Fisher from. But we've also moved into the laboratory area where we've got labs, assay, air, gas, radiation, monitoring, water equipment, all servicing the mining industry. So I would hazard a guess, as I said, where most of you are listening today, you're somewhat familiar where our online analyzers and sensors can add value to your operation. The most common are in the metalliferous operations like copper, nickel, lead, zinc, etc., as well as our particle sizers and samplers in the same operations, but also in a large number of gold operations as well. But it also includes the bulk industrial operations, iron ore, phosphate, magnesium, manganese. But it also operates in areas such as, sulfide versus leach discrimination in value-based ore control. Can assist in laterite operations, both nickel and bauxite, gold, but via improved process control and opportunities. It is not in direct online measurement of gold. Or maybe in stranded and satellite deposits via bulk ore sorting. You remember, deliver less waste and more metal. Or it could be as simple as logistics and cost reduction in bulk commodities. You don't want to freight silica around the world when really you want more metal. Or it's quite simply, it's improved product quality control applications. I kind of think about it, sometimes it comes down to you don't actually know what you don't know. So the opportunity is to turn data into knowledge and knowledge into actionable outcomes that then will generate more cash. So today we are looking at the Thermo Fisher online analyzer family that can aid in meeting our goal of less waste and more metal. We will touch on the XRF analyzer of families and then move on to the PG&A family, which from practice we tend to find people are less familiar with. So the XRF analyzers can only measure heavy elements, and Garry will talk about what heavy elements means in a few minutes. But you have the ANSTAT, which is effectively an all-in-one analyzer and sampling station. Great for single streams from a few cubes up to 35,000 cubes an hour. We have the centralized analyzers such as the MSA or the multi-stream analyzer. It's great for where you have low headroom or vertical restrictions maybe. Or you have the LScan that can read up to 24 streams, but it has a smaller sort of XY footprint that will enable it to fit into older analyzer spaces. And then you have the PG&A family, which can analyze both light and heavy elements, but may have an alternate business use or business case. But in saying that, I also want to highlight, don't fix what isn't broken. XRF analyzers, they're a tremendous tool and they will meet a vast requirement of your business needs. They're quick, easy, reliable, and they'll work perfectly well. But if your business needs actually go beyond the remit of what XRF is capable of delivering, then you may need to look at PG&A analyzers. This means your area of opportunities may include light elements like silica, phosphorus, sulfur, for example, or light elements and heavy elements, but in a location that XRF can't operate. So that may include on a conveyor after the primary crusher. That's a great spot before you spend loads of cash grinding waste in the mill. Remember, it's about less waste and more metal. But I suppose the simple why PG&A can work for you is simple. Air gap and water is basically the enemy of XRF. That's why XRF operates in a slurry where the sample is literally in contact with the XRF analyzer in the slurry sample. But Garry will elaborate more on this for us now.
Thanks, John. I trust everyone can hear me. I was having some troubles joining. You hear me okay, John? Yep.
Gotcha, mate.
Excellent. All right. Well, when it comes to the solutions that work, PG&A online analyzers have a proven history of delivering solutions to a wide range of applications for over 40 years, with Thermo Fisher Scientific having installed well over 1,500 analyzers globally. I know this because I've been a PG&A physicist for over 25 of those years, developing PG&A solutions and helping customers to realise the benefits of this real-time analytical technique. We are seeing emerging needs and challenges in mining and mineral processing, for example, associated with declining grades, increasing ore complexity and variability, which require new measurement solutions that PG&A online analyzers are well suited to solve. So what is PG&A for those who may not be familiar? It stands for Prompt Gamma Neutron Activation Analysis, and it's a measurement technique that uses a source of neutrons, which are emitted into a sample. The neutrons then collide with the nuclei of the elements in the sample, which causes the nuclei to be excited to a higher energy state, which then promptly returns to a stable state, emitting one or more characteristic gamma rays. It's a similar concept to another more familiar technique to some, XRF or X-ray fluorescence, which uses X-rays to interact with the electrons surrounding the nucleus, exciting the atom by knocking out an electron from a lower energy shell, which results in a high energy shell electron filling that vacancy and emitting the excess energy as a characteristic X-ray. One of the key differences with PGNAA is that both neutrons and gamma rays can penetrate entire rocks and sample depths up to hundreds of millimeters, compared to only a few microns of penetration for X-rays. So it can provide representative analysis of large volumes of material independent of particle size. Another key difference is that there are no matrix effects as seen in XRF, since in PGNAA the input, neutrons, and the output, gamma rays, are independent, whereas in XRF, an X-ray emitted from a heavier element, higher than calcium on the periodic table, can excite lighter elements lower on the periodic table before reaching the detector, which impacts the detected X-ray spectrum and often requires recalibration for changes in mineralogy. PGNAA doesn't suffer the same issue with changing mineralogy. Since PGNAA can penetrate the entire sample and is independent of particle size, it can measure the entire material flow on conveyor belts, not just the surface, and can measure large volumes, tens of litres, of slurry independent of particle size distribution. Other technologies such as XRF, XRD, and other spectral or laser techniques have very limited penetration, which prevents online analysis of coarse particles and lighter elements, typically below calcium. Lab analyzers using these techniques require analysis under vacuum or in a helium-purged environment to measure light elements accurately, which is obviously not possible for online measurement. PGNAA, however, can accurately measure both heavy elements above calcium and lighter elements online, enabling real-time analysis of sulfur and light elements associated with gangue, which impact process control and metal recovery. So measurement technique alone does not ensure a solution that works. Unlike laboratory analyzers where samples are prepared and presented to the instrument in a consistent and uniform manner, online measurements must be designed to perform under varying material flow conditions. To achieve a representative laboratory analysis, the first step is to take a representative sample based on theory of sampling, which requires that every particle in the stream has an equal probability of being included in the sample. To achieve a representative online measurement, it follows by extension of the theory of sampling that every atom that passes through the online sensor must have an equal probability of being included in the analysis. Otherwise, you can introduce a measurement bias. Thermo Scientific PGN analyzers are designed to optimize uniformity of measurement, as shown in the top left image. However, other PGNA analyzer designs do not deliver measurement uniformity. The example in the top right shows an analyzer design with a centered source and detector configuration. Some designs have the neutron source on top and detector below. Both provide poor lateral and vertical uniformity, which can therefore introduce measurement bias. Other measurement techniques used online on belts and on shovels only provide surface measurements, so would only measure the surface layer of the material or the surface of falling rocks. In either case, every element below that penetration depth will certainly not be included in the analysis and would almost certainly introduce measurement bias. So calibration methodology is also critical to ensure accurate online analysis that accounts for the full range of material flow conditions and chemistry and mineralogy variability. So you might be familiar with the 5 Ps. Proper preparation prevents poor performance. This encapsulates our approach to online PGNA analysis. The first step is in the preparation and gathering the relevant conveyor and material flow conditions and information on the chemistry and variability, mineralogy variability. Gathering this information ensures that every analyzer we supply undergoes a full factory calibration across the full chemistry range and belt loading range. We use modular reference standards that span the full chemistry range, and the modular standards enable calibration across varying belt loads to be simulated to simulate the variation in flow when installed on site. We then incorporate this into our automatic belt load calibration to ensure that we provide results online when it's installed on site that's independent of the flow rate. So we use manufactured reference standards to ensure the full range of chemistry is fully spanned. Experience has taught us that it's very difficult to obtain customer material samples that span the full range of every element, and using such samples would compromise the calibration. These plots show the copper and sulfur ranges for the manufactured reference standards, shown here with the red plus symbol, compared to the narrower range samples we obtained from Newcrest, shown here with the green crosses. These were measured during the factory calibration of the CB Omni analyzer we supplied to Red Chris, and which was installed in 2023. So here we have a photo of the installed CB Omni at Red Chris, and as you can see, it's measuring run-of-mine feed with the neutrons and gamma rays fully penetrating these rocks to enable real-time analysis of the entire material flow. The reference standards shown in the previous slide were measured during the factory calibration and then shipped to site with this analyzer, and we measured them on site during the commissioning to validate the performance that we achieved in the factory. At Red Chris, they were able to utilize existing upstream and downstream data sources to validate the CB Omni performance. They used upstream grade control and truck haulage data and downstream flotation feed slurry assays. They carefully accounted for the time delays associated with these different data sources to align the data and provide this graph, which gave them confidence that the analyzer was accurately reading the feed that they were sending into the process. So this demonstrates that using the 5 Ps and careful analyzer design and calibration methodology, it is possible to deliver online solutions that work, providing immediate value following installation and commissioning without the need for lengthy and costly on-site calibrations. So the considerations I've talked about up to now relate to the process variables on site that a PG&AA supplier can't generally control. However, there are considerations that can be controlled and that do impact the value a PG&A analyzer can provide. One thing the manufacturer can control is the neutron source output capacity. Ultimately, it boils down to, for an analyzer that is designed to accommodate a larger neutron output, you'll get more gamma rays generated, and the more gamma rays you generate, the better the precision you can achieve. So the neutrons are needed to produce the gamma rays. However, once you've produced them, you've got to detect them. So Thermo Fisher Scientific PG&A analyzers use a 4x4x16 scintillation crystal. Some other PG&A analyzers use 3-inch by 3-inch cylindrical crystals. Just from the volume calculations, you can see that the larger crystal is up to 12 times larger in volume. Larger detectors can detect more gamma rays, and the more gamma rays you detect in a given time frame, the better the precision. So why does this matter? In real-time blending control applications or bulk ore sorting applications, it matters a lot. The plots here are from a paper I presented in 2020. Here I was looking at a bulk ore sorting scenario with a representative copper grade distribution and a 0.2% copper cutoff grade, where we reject everything measured below 0.2% as waste. These plots here represent 2 analyzer configurations. On the left, the equivalent of 4 Thermo Fisher detectors and 78 micrograms of californium. And on the right is equivalent of only 1 detector, and which is equivalent of 12 smaller volume detectors and 50 micrograms of californium. In any measurement scenario, you'll always correctly measure some ore as ore and waste as waste, but you will also inevitably misclassify each. However, the proportion of misclassification of ore as waste and waste as ore is dependent on the analyzer performance, in particular the precision. So a poorer precision analyzer will misclassify more material, thereby rejecting more copper as waste and sending more waste to the mill. In the 2020 paper, I presented a case based on a simulated 40,000 tonnes per day plant. In this case, compared to the higher precision analyzer, the poorer precision analyzer would send an additional 200 kilograms of copper per hour to waste, which would amount to millions of dollars per annum. So if you want less waste and more metal, it pays to invest in solutions that work better than others. I'll now hand back over to John to provide an overview of where PG&AA can be deployed.
Thanks, Garry. If we move, here we go. Probably move. I've clicked twice, so let's see what happens here, folks. Look, so there's a lot to take on board there about why it can help you, but the why is actually really important to understand for the where it can assist you, because what we want is less waste and more metal. even though I've spent 30 years in mining operations, I've operated bulk ore sorters and have worked in deploying mining technology into operations, I kind of inherently knew how it could work. But in saying that, it's actually quite difficult to summarize it in a meaningful way. So what I've tried to do here is simply group it into some bins that we'll discuss in the next few slides. Garry will run through PG&A applications on conveyors for basically blending control, and then he'll move into slurries for flotation. I'll then wrap up with a few comments about bulk ore sorting and some precious metals, but we don't have time to discuss all the solutions or potential applications here. But feel free to give us a call, and if any of these other applications may be an interest to you, give us a call and we'll have a chat. Otherwise, back over to Garry.
Thanks, John. Yep. Okay. So here we have, sorry, skip forward an extra slide. Right. So blending control applications. So blending control applications have been the cornerstone of PG&A applications for the past 40 years. In particular in cement, where PG&A is used for blending stockpiles to a target, or proportionally blending stockpile material with corrective materials to achieve consistent kiln feed, which ultimately delivers consistent quality cement. And in coal, it's been used to measure sulfur and ash and blend to targets needed for coal-fired power stations. And more recently, in the steel industry, PG&A analyzers have been used in blending control for basicity control. So iron ore fines are blended with limestone, and PG&A analyzers have been used to produce more consistent quality sinter for the downstream blast furnace. So here we have the process flow diagram for a typical sinter process, where raw materials are blended in that top right corner. That material is then fed onto a sinter strand, where the sintering can take up to about an hour, after which the sinter is then cooled in a cooling ring. That also takes about an hour, and then samples are taken of that cooled sinter before it then is sent to the blast furnace. So samples are typically taken 2 hours after the raw material blending stage. Including the lab turnaround time, the traditional control feedback loop is several hours, during which time the raw materials, the chemistry might have changed significantly. So this process flow diagram shows the same process, but with a CB Omni Agile located before the sinter strand, enabling real-time control of the limestone addition to achieve a consistent calcium-silica ratio. The feedback loop is reduced to minutes. This results in a more efficient sinter process, which uses less energy and reduces the raw material costs. It results in more consistent quality sinter, which means less corrective quartz or limestone addition at the blast furnace, and results in improved hot metal quality. So ultimately, less waste and more metal. I can see parallels with other smelting applications, example being copper. Direct measurement of sulfur, iron, and copper can enable blending control of the concentrates, and also measurement of the silica can be used to directly control the silica addition to achieve consistent iron-silica ratio. In flotation processes, PG&A slurry analyzers are also used, and PG&A can add value where light element measurement can enable more effective control of the process. For example, in copper flotation, being able to measure sulfur, iron, and copper, along with the ratios between these elements, enables changes in sulfide mineralogy to be seen and enable real-time control actions to improve recovery. Light elements associated with clay and talc or relating to acid neutralization can be measured and therefore better controlled. PG&A can also add value in reverse flotation, for example, in phosphate and in iron ore. In iron ore, it enables real-time control for producing low silica concentrate for pellet production used in producing green steel. So the GS Omni is a multi-stream PG&A slurry analyzer, able to measure up to 8 streams. It uses the same proven technology as the cross-belt PG&A analyzers, however, incorporates a multiplexer to sequentially measure sampled streams. Again, the differentiator between traditional online XRF slurry analysis being the ability to measure those lighter elements, and it's not limited by particle size. So here we have an example of the iron ore reverse flotation process, where a GeoSomni makes it possible to measure feed, concentrate, and tailing streams, including on multiple process lines. And this enables real-time control of reagents for reverse floating the silica and suppressing the iron to achieve higher and more consistent iron concentrate and control iron loss to tailings, again resulting in less waste and more metals. I'll hand back to John now to discuss some other PG&A application opportunities.
Thanks, Garry. Okay, so if we look at the highlighted opportunities here, it covers numerous deployment methods on a conveyor belt. From bulk ore sorting, which in various forms really equates to essentially rejecting waste pods and replacing those pods with low value waste or low value pods and replacing it with higher value ore. The PG&A can also be useful in conveyors in other ways. But in saying that, I'm going to say it's important not to get stuck into what I call the proof of concept prism. That's simply because it's a business case opportunity analysis. It is not technology constrained. Every solution is individual to a mine site and that site specific processing requirements, but it could include opportunities like bulk ore sorting, where we're sensing and diverting subgrade pods. It's the same as a grade control SMU, or the smallest mining unit, but now we're calling an SDU, a sensor diversion unit. We want to reject value destroying or deleterious ore types. We want to enhance the viability of satellite deposits or enhance the economics of overland conveyors, or even just simply bulk logistics and transport decisions. It could include simply real-time intervention at the mining face. If there's really something wrong in grade control, you can do something about it straight away. Optimize those processing pathways, leach pads versus sulfide mill. Because you can measure the gangue, you can define the oxides versus the sulfides, fresh versus oxidized. You can back calculate the mineralogy via elements, and you can determine grind optimization via hardness of that gangue mineralogy. You can optimize the flotation and mineralogy beyond what you can do with XRF. And that might include pulling some of those intervention opportunities like residence time, pH, grind, dosage, or any of the gangue or light elements that are available when you're talking beyond the XRF remit. You can use it in mine-to-mill reconciliations. But it's remember, don't fix what isn't broken. Think what is beyond the XRF constraints and what you can do to reduce waste and create more value. So in this case, we're actually looking at an example based on a porphyry copper. The upgrades are based on a bulk ore sorting plant where I was operating. We were rejecting about 10% of the tonnes on average, variable, but let's say rejecting 10%. And we were getting a variable upgrade, but it was averaging about a 10% upgrade to the mill. But what this does do equates to about an extra 8 kilotonnes of copper. So using today's copper price, that actually equates to about $100 million of additional revenue. That is sensational, no two ways. But as you can see here, there is no such thing as a free lunch, and there are real costs that still need to be deducted from that. And you still need to be capable of replacing that reject with higher value ore. Not mentioned here, but are very applicable, are further upsides. There's increased recovery, which is commonly associated with grade, increased throughput through hardness and grind from the back calculation of the mineralogy, reduced processing costs through stability of operations and dosage rates I just mentioned. But it may even be the ability to respond to abnormal operating conditions. You might want to choose a high grading strategy through periods of reduced power or water availability. And there's also simply ESCG requirements where you may want to maximise the value from the resource And now you can start operating in marginal ore or even in those low-grade stockpiles. So in other words, it's trying to open up opportunities for less waste and get more metal. But in bulk ore sorting can operate in fixed plants, operating at greater than 10,000 tonnes per hour. But that is actually simply an engineering capability, and it's a business case analysis for the most appropriate location to do that. Once again, it's not a technology constraint. Alternatively, as we're looking at here, you might look at a modular low capex plug and play, which is something we're currently designing with our business partner. It's far more suitable for satellite deposits or maybe in stockpile locations rather than on the main primary coarse ore stockpile. The greatest strength of this configuration is 100% of the components, the mobile crusher or sizer, the PG&A analyzer, and the integrated stacker and flop gate, they're all truck deliverable to site. There's minimal to no civil works. Plug into the mains and genset and play. The configuration shown here is simply limited by the size of the PG&A unit we've put in the C container. But that said, it's still configurable from 200 to 300 tonnes and up to 1,200 tonnes per hour in the configuration seen here. So it's not huge, but in saying that, it's not boutique throughput either. But it's also an ideal scenario to test the business case that's offline away from your main primary crusher and the main conveyor into the mill. But you can have primary comminution, sense and separate on site, quick and easy for a low capex or a low opex option as well. Right, so the last time you need to look at this slide, and I know some PG&A suppliers claim you can measure gold or precious metals. Well, I'm going to say technically you can, depending on your operation. But if your mine's operating a couple of 100 grams per tonne, right, let's talk. But if it's not, and you're talking at grams per tonne or less, then PG&A will not measure gold and PGEs directly that allow you to take any meaningful actions. But look, if you want to know you sent 0.5 gram per tonne to the mill over the month, yeah, well, maybe, but I'll be honest, that's what grade control does. And it's a much better tool for that opportunity. But it doesn't mean it's not capable of delivering actionable information that allows you to process less waste and more metal. For example, in autoclaves, the battle is really about sulfur and sulfide. It's actually nothing to do with gold almost. PG&A can measure sulfur particularly well. If you're generating a sulfide con for export or ultrafine grinding, then really it's all about getting real-time sulfur control to optimize the floats. There's no point getting a shift composite back the next day to realize you've been sending all this sulfur, i.e. gold, to the tailings dam. You need to know that at the time so you can take actionable tasks at the time to maximize your gold recovery. Likewise, it might be bulk ore sorting via proxy. Example, maybe arsenic with gold or nickel and copper with PGEs. But I suppose a few takeaways I'd like people to remember is what actionable task could be undertaken if you have the data to process less waste and recover more metal. It may be as simple as better quality product control or improved efficiencies, but don't fix what isn't broken. XRF is an excellent tool, but it does tap out at calcium when you get down to the light elements. So if you want actionable data for light elements that XRF can't deliver, either as a coarse product on the conveyor belt or as a ground slurry and process plant and tailings, then maybe PG&A is for you. Mining, crushing, grinding and separation, it does cost a bomb. So think about less metal. That'd be more about less waste and more metal and the solutions that work. Yeah, but look, thank you for your time. And if there's any questions, Gary and I would love to hear back from you and see if we can answer any of your questions.
Great. Thank you so much, John and Gary, for sharing your industry expertise and Thermo Fisher technology with us this afternoon. For the audience, thank you again for being here. But we do have time to take your questions. So if you would like to submit a question for either John or Gary, you can submit that using the Zoom interface. But to get us started, I do have a few prepared questions for you both. So I'll go ahead and get us started with that. All right. So, John, what are the biggest challenges or roadblocks to PG&A in bulk ore sorting?
Yeah, very simple, but a huge number of answers there. So we'll just have to sort of just pick a couple. Look, one of the biggest constraints is it's bulk ore sorting. It's not easy to do a quick trial. There's no sort of we can just go grab a few rocks and do a quick lab test. So that is one of the major constraints, just be able to have the confidence of doing lab tests of how to deliver, because it's all about heterogeneity. You've got to have different pods on the conveyor as delivered after the crusher. So there's a lot of modeling involved there, but it's generally low risk, but it is a constraint. And I'm just going to pick one of the others, which I'm going to say is quite a common problem, is once we move into technology, we've got a machine that goes ping. And whenever we've got a machine that goes ping, it seems to think like it has to be perfect, but it doesn't have to be perfect because we're bulk ore sorting. And that being said, technology cannot replace good quality work. And some of the cases I've been using bulk ore sorting, they've been trying to use the technology to replace what I'm going to call good geology practices 101 and good mining practices 101. Example, like the best way to separate ore and waste is get your assays back in time for your blasting, follow your SOPs, put a V in the right spot in the blast to separate ore from waste. That is going to provide the biggest higher value before you do anything. But then trying to use, say, a bulk ore sorter to separate ore and waste without doing first pass mining 101 practices, it's not going to succeed. You know, it's horses for courses. Do your best practices first. So that's two. Like technology can't replace good practices, full stop. And the challenges of modeling it and then testing it in real time is a constraint.
Can I just add one more comment there, John? In the case of the analyzer we have up at Red Chris, each truck that dumps its ore, what's considered ore that's been sent from the mine to the plant, one truckload of material, once that's gone through the crusher and then onto the conveyor belt, it equated to about 6 minutes or 1 kilometre of material stretched out over that belt. That was equivalent to one truck. So we're measuring that rock from that truck in real time. And with the blasting, the haulage, the crushing, there's sometimes people think that all the variability gets blended out, but in that 6 minutes we were providing sort of minute by minute analysis. We could see variability within each truck, so that highlighted that there was even within one truck there's potential to segregate and divert low value material that's within a truck that on average is above grade, but there's actually low grade opportunity to divert.
Right, thank you both. Another question that we have for you is, can you directly measure mineralogy with PGNNA and AA technology?
Yeah, thanks. I'll take that one to start off with. So PGNAA is an elemental technique. Same with XRF. There's a lot of techniques that will just measure elements. However, by measuring the lighter elements that XRF can't measure, for example, and in particular for, say, sulfide mineralogy, measuring sulfur directly and then being able to measure the copper and the iron, we can look at the ratios of those elements to each other, and that gives us some insight as to the sulfide mineralogy. So if we see those copper sulfur, copper iron, iron sulfur ratios changing, it tells us that something's changing with the mineralogy. And typically with XRF, certainly on stream slurry analyzers, if you only have the iron and the copper available to you, you can't quite solve the puzzle. But we can provide all the pieces of the puzzle now with PGNAA, and that does enable mineralogy to be inferred by looking at those ratios. I guess just to add to that, the lighter element analysis associated with the gangue can also provide some insight into perhaps the mineralogy. So Red Chris has certainly started looking at trying to infer hardness, looking at the potential acid neutralization. So there's things that you can start to unpick from the elemental analysis to give you insight into not only the sulfide mineralogy you're delivering to the plant, but also the gang that might be causing issues downstream. And you can start to take real-time preventative actions, or you can start to react to that rather than only see the result down the track with a post-analysis, if you like.
Great. Thanks for that, Garry. I think we have time for one more question, and I'll let you all decide who should answer it. What does the calibration mean for getting up and running of the main conveyor? Is it a day or a week, or what's that time frame look like?
I can kick off with this, I guess, the factory side of it. John's had some experience in the field, so I guess I talked about the 5 Ps. Proper preparation prevents poor performance. So we put the work in up front in the calibration, the factory calibration. We do that that preparation, which takes us weeks in the factory, and that results in an analyzer that gets delivered to site and is ready to go as soon as you've got it installed, pretty much. So that then the on-site work is only days. So installation can take 1 to 2 days to get the analyzer physically installed. The reference standards that we supply, which enable validation that the delivered analyzer is still functioning as it was when it left the factory, that takes a day or two. So it's a matter of days on site, and you're up and running. So, I mean, John, I don't know if you want to add any comments there.
Yeah, I suppose the big differentiator from my past experience is, like Garry said, you install it on a planned shutdown, right? So planned shutdown, you physically install it and it's in on a planned shutdown, end of story. Now, if you got time, let's say you need another 24 hours to do the confirmation calibration, if you like. Now, if you haven't got that, your shutdown is you got 3 shifts to install it. You install it, it's done, it's finished. Turn the conveyor back on, you're feeding the mill, because that's the key. You can't not feed the mill. Well, it's up and running. As soon as you turn it on, the PG&A analyzer is up and running, as soon as it's installed, and it's delivering results. Now, if you want to do the confirmation calibration, you just do that on your next planned shutdown. Now, if that planned shutdown is on maintenance and the conveyors on the following weekend, well, you just do the calibration on the following weekend. If that's not for another month, you do it in another month's time. But the point is, you install it, as soon as the mill's up, it's up and operating the same time, the same day. So there's no delays in turning on and operating. Post-calibration, whenever your next planned shutdown is. And that's a key driver, because no one is going to stop the mill for you to calibrate a PG&A sensor and stop the primary crusher and stop feeding the mill. And there's no need to do so. It's up and operating as soon as it's physically installed. And that's a big differentiator.
Great, excellent. Thank you so much. Well, since that's all the time that we have for questions, I'll now go ahead and wrap us up. I'd like to give a big thank you to both John and Garry for your time today, and also to our audience for taking time out of your busy day to be here with us. And as a reminder, this has been recorded, and we will send you the link to the presentation for you to access, or it'll also be on the OSMine YouTube channel. So thanks again for joining us. I look forward to welcome you to another OSMine webinar in the future. And I hope you all go out and enjoy your day. Thank you.
Thank you.
Thank you.